For decades, our galactic maps portrayed black holes as static gravitational anchors, locked within the dense cores of galaxies or orbiting in predictable binary systems. This assumption of stability has been shattered by recent astrometric data confirming the existence of a vast, invisible population of rogue wanderers. These are stellar mass black holes that have been violently ejected from their birthplaces, traversing the interstellar void at velocities exceeding 400 kilometers per second. To understand how an object with such immense mass becomes untethered, we must look at the chaotic physics of its creation, the core collapse supernova. When a massive star reaches the end of its life, it does not always explode with perfect symmetry. Theoretical models and observations of pulsar proper motions suggest that the explosion is often anisotropic, meaning the force is distributed unevenly across the surface of the dying star. This asymmetry creates a phenomenon known as a natal kick. Following the law of conservation of momentum, if the majority of the supernova's matter or neutrino emission is blasted in one direction, the remnant core, the newborn black hole, must recoil in the opposite direction with equal force. The implications of these kicks are profound because the majority of massive stars form in binary pairs. Population synthesis models indicate that nearly 80% of these massive binaries will eventually dissociate or break apart due to the violence of the primary star's death. If the kick velocity is high enough to overcome the gravitational binding energy of the system, the black hole is launched into the galaxy as a solitary traveler. Unlike Gaia BH1, which resides just 1,500 light-years away in a stable orbit, these kicked remnants have no companion to illuminate them. Detecting these dark nomads requires a reliance on gravitational microlensing. This technique relies on chance alignment. As a rogue black hole drifts between Earth and a distant background star, its gravity acts as a lens, temporarily magnifying and warping the starlight. However, identifying these events comes with significant epistemic uncertainty. The primary challenge lies in distinguishing a low-mass black hole from a massive neutron star or an old faint white dwarf, as the lensing duration depends on both mass and velocity. Without a binary partner to provide orbital data, determining the precise mass of the lens is difficult. A confirmed detection requires the calculated mass to strictly exceed the Tolman-Oppenheimer-Volkoff limit of approximately 2 to 3 solar masses, the theoretical ceiling for a neutron star. Despite these detection challenges, the statistical probability is staggering. Based on the rate of star formation and death in the Milky Way, astronomers estimate that millions of these isolated black holes are currently drifting through our galactic neighborhood, largely inert and undetectable. It is crucial to clarify that these stellar mass rogues are not cosmic vacuum cleaners aggressively hunting matter. Without an accretion disk or a nearby star to feed on, they are gravitationally dormant, interacting only if a system passes directly within their immediate sphere of influence. While the mechanics of stellar kicks are well understood, a far more terrifying phenomenon occurs when galaxies themselves collide. In the next section, we will analyze the mechanics of the superkick, a gravitational wave event capable of ejecting supermassive giants relative to the mass of millions of suns. While supernova asymmetry is sufficient to eject stellar mass objects, launching a supermassive black hole from a galaxy requires a disruption of space-time itself. This mechanism is known as gravitational wave recoil. It occurs during the final chaotic moments of a galactic merger as the central black holes of two colliding galaxies spiral toward an inevitable crash. As these titans orbit, they emit intense gravitational radiation. If their masses are unequal or their spin vectors are misaligned, this emission becomes highly anisotropic, beaming energy predominantly in one direction. Momentum conservation dictates that the newly merged black hole must recoil in the opposite direction, acting like a cosmic engine thruster powered by the curvature of space. The resulting superkick can accelerate a singularity weighing millions of suns to velocities exceeding the galaxy's escape velocity, permanently ejecting it into the intergalactic void. Theoretical models have predicted this violent separation for decades, but observational confirmation remained elusive until the James Webb Space Telescope turned its near-infrared spectrograph toward a peculiar linear anomaly. In a 2025 analysis, astronomers characterized a streak of shocked gas extending 200,000 light-years, physically linking a distorted host galaxy to a massive bright point source. This feature was not a relativistic jet fed by a stationary accretion disk. The spectral data revealed a wake of ionized hydrogen and oxygen consistent with a bow shock moving through the circumgalactic medium. The culprit is a rogue supermassive black hole, estimated at 20 million solar masses, tearing through the gas at a staggering speed of 2.2 million miles per hour. The physics of this wake are counterintuitive. Rather than simply consuming the material, the black hole's passage compresses the gas, triggering a rapid chain reaction of star formation. This process leaves behind a distinct contrail of newborn stellar clusters, effectively marking the path of the fugitive object like breadcrumbs leading away from the galactic table. Scientific scrutiny demands we consider alternatives, such as a collimated jet from a hidden active galactic nucleus mimicking a wake structure. However, the absence of an opposing counterjet and the presence of hyper-compact stellar associations at the precise tip of the linear feature strongly favor the ejection scenario. This phenomenon is not unique to giants. In September 2025, a smaller black hole was found displaced by over 3,000 light-years from the core of a dwarf galaxy, still emitting radio waves. These discoveries prove that galactic centers are not permanent cages, and the universe is populated by unbound titans moving at relativistic speeds. The JWST Runaway was visible only because it crashed through a gas-rich environment, but most rogue black holes travel through the dark silence of the void, completely undetectable until they shred an unlucky star. For the vast majority of wandering black holes, this darkness is absolute and permanent, rendering them effectively non-existent to our current observational instruments. However, the silence of a rogue supermassive black hole is broken the moment a star inadvertently crosses its tidal radius. When a star passes this critical threshold, the gravitational differential across its body becomes extreme, with the side facing the black hole experiencing a pull significantly stronger than the far side. This tidal force exceeds the star's own self-gravity, instantly overcoming the binding energy that holds the stellar core together. The result is a tidal disruption event, or TDE, where the star is not simply swallowed, but spaghettified into a long, thin stream of stellar debris. Roughly half of this material is ejected back into space, while the remainder spirals inward, forming a transient accretion disk that flares brightly in ultraviolet, optical, and X-ray wavelengths. In May 2025, astronomers using wide-field optical surveys identified a transient signal that perfectly matched this violent profile. Designated AT-2024-TVD, this event occurred approximately 600 million light-years away at a redshift of z equal to 0.045. What made AT-2024-TVD anomalous was not the brightness of the flare, but its location relative to its host galaxy. Standard supermassive black holes reside exclusively in the galactic nucleus, the gravitational anchor of the system. This event, however, was located at a projected offset of more than 3 kiloparsecs from the core. A displacement of 3 kiloparsecs places the object roughly 10,000 light-years out into the galactic suburbs, far from where a supermassive black hole should theoretically exist. This significant offset provided the strongest evidence to date of a recoiling giant, likely ejected by a past merger event. Scientific rigor demands ruling out alternative explanations, specifically the possibility that this was merely an exotic supernova occurring in the galaxy's halo. To distinguish a rogue black hole from an exploding star, astrophysicists analyze the evolution of the light curve over time. A supernova's brightness typically decays according to the half-lives of radioactive isotopes like nickel-56. In contrast, AT 2024 TVD displayed a decay rate following a precise power law of T to the power of -5/3, the theoretical signature of accretion fallback onto a black hole. Another confounding variable is the line of sight probability, where a background galaxy hosting a central TDE simply aligns visually with the outskirts of a foreground galaxy. High-resolution imaging and spectroscopic redshift analysis were required to confirm that the flare was indeed associated with the halo of the foreground system. The confirmation of AT 2024 TVD validates predictions made by cosmological simulations such as Romulus, which model the chaotic evolution of galaxy clusters. These simulations suggest that for every galaxy we see, there may be hidden wanderers lurking in the halo, with estimates reaching hundreds of rogue supermassive black holes per cubic volume of 100 megaparsecs. This implies a fundamental shift in our understanding of galactic anatomy. A galaxy is not just a visible disk of stars and gas, but a complex structure containing a scattering of invisible, hyperdense engines ejected during the violent history of hierarchical assembly. These detections are crucial for solving the problem of missing baryonic mass in the universe. By mapping the frequency of offset tidal disruption events, we are slowly building a census of the dark population that exists between the stars. It is important to correct the misconception that rogue implies erratic or unpredictable motion. These objects follow strict ballistic trajectories determined by the laws of general relativity and the initial recoil velocity. They are not hunting, they are simply drifting on ancient, immutable paths. As observational baselines increase and the sensitivity of instruments like the Vera Rubin Observatory comes online, we expect to find thousands more of these offset flares. The universe is far less static than our maps suggest, filled with invisible giants moving silently through the void. Ultimately, the study of rogue black holes reminds us that stability in the cosmos is temporary. Even the most massive objects in existence can be untethered, forcing us to rewrite the history of galaxy formation to include these wandering titans.